This will be video 7 of Unit 4, and in this final video we'll talk about something called orbital notation. Remember, we've been talking about how electrons are arranged around the atom, and this is the more detailed view of how that looks like. What we'll do for this type of notation is we'll draw lines, or sometimes boxes could be used, above each of the subshells to represent how many orbitals each subshell has. So these lines will represent orbitals. And in these orbitals, we'll have to draw our electrons. Now, the S subshell has one orbital, remember? So here it is. The P subshell has 3 orbitals. The D subshell, remember, has 5 orbitals. And the F has 7. So it's a good idea to remember how many orbitals in each subshell. What we'll do then is we'll draw electrons in there. And before we do that, let's go through something called spin. Electrons can have a property called spin, and it could either be positive or it could be negative. We'll represent the positive spin with an up arrow, the negative spin with a down arrow. So think about the idea that electrons, as they're zooming around the atom, here's the nucleus, and as the electrons are flying around the atom, they have a spin to them. So think of the electron as spinning on its axis. That's the way. They can either spin clockwise or they can spin counterclockwise. That's a good representation of what we think it is, even though that's not the exact thing, but we'll represent it with up and down arrows. And you'll probably see me draw half arrows up, half arrows down. It's easier to draw them that way. So the rule is this. We'll first add one up electron to every one of the subshell. Apologize. To each orbital in a subshell, and then we'll add the down electron until the subshell is filled. In other words, we're going to take a look at one subshell at a time. So we'll add the up, and then we'll add the down. Then we'll take a look at the second subshell, the 2s subshell, one up, one down. And then looking at the third subshell, we'll first put the up electrons in, and then, if needed, we'll put the down electrons. And it's a good idea to recall what we mean by orbitals. Remember, orbitals are these 3-dimensional shapes around the nucleus where the electron can be found. And for us, we just said, think about these as 3-dimensional balloon-like shapes. So for carbon, for example, carbon has the 1s orbital, the 2s orbital, and 3 2p orbitals, 2 of which have electrons in them. The third one does not have electrons. So we're actually going to do an example of this, and it'll probably make more sense. So why not we do this one? Let's write the orbital configuration for oxygen. So let's write out first oxygen's full electron configuration the way we've done it before. And oxygen should have a total of 8 electrons around it, which will require 1s2, 2s2, and 2p4. So just like before, we'll write the electron configuration, and then below each of these subshells that we've written, we'll draw lines representing orbitals. Each s subshell has one line, one orbital. Same thing for this one. Each p subshell has 1, 2, 3 lines. And now we'll put the electrons in the lines. We'll have to work one subshell at a time. Let's work the 1s subshell. It has 2 electrons. So we'll put 1, 2. You'll first put the up arrow, then the down arrow. With the 2s, same idea, up, down. With the 2p, we have 4. So the rule says put all the ups in, and then come back and put the downs in. So 1, 2, 3, and then come back and put the down in. And the important thing is, you see there are 2 orbitals that don't have a pair. And you'll see later that oxygen, for example, forms 2 bonds. Here is oxygen forming a bond with water. So one of the bonds is with this hydrogen, the other one is with this hydrogen. And this is due to the fact that oxygen has 2 available orbitals for bonding. You don't have to understand this idea, but realize that these orbitals connect to the bonding later on. Let's do the same thing for chromium. In this case, I'm actually going to do chromium's full configuration, and then we'll do a shortened version, the noble gas configuration. So here's chromium. Take a look at chromium from the periodic table. It should have 24 electrons, which means we'll have 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2, And finally, I'll put it down here, 3d for chromium, 3d4. All right, well, let's go ahead and write out the orbitals for each one of these. Every s subshell has one orbital, so for every s, I'll draw one orbital. For the 3s, one orbital. For the 4s, one orbital. Every p has 3, so I will draw 1, 2, 3. 1, 2, 3. I know it's getting a bit crowded. Every d has 5. 1, 2, 3, 4, 5. By the way, the way to remember this from the periodic table, here's your periodic table. Here is your periodic table. If you take a look at the s block is 2 elements wide. And because 2 electrons go into each orbital, that creates one orbital. The p is 1, 2, 3, 4, 5, 6 electrons wide. Since an electron goes into, 2 electrons go into one orbital, that gives you 1, 2, 3 orbitals. The d is 10, and since each orbital holds 2, you get 5 orbitals for the d. So in other words, you have 1 orbital for the s, 3 for the p, 5 for the d, and yes, 7 for the f. That's a way to memorize it using the periodic table. Okay, so now let's go ahead and complete this. Let me redo a little bit here so it's a little easier to follow. What we'll do is, as before, we'll fill in the orbitals one subshell at a time. So let's take a look at the 1s2 subshell, 2 electrons, 1, 2. The 2s, 1, 2. The 2p have 6 electrons, so put the ups in first, and then put the downs in. You have to do it this way. 3s2, 2 electrons, up, down. 3p6, 6 electrons, 1, 2, 3, 4, 5, 6. 4s2, 1, 2. And then the 3d, we have 4 electrons. We'll do 1, 2, 3, 4. Now notice if you didn't follow the rule of putting the ups in first, but decided to double them up right away, you get a different picture. You'll get 1, 2, 3, 4. This is the wrong picture. You have to put the ups in first. And this is due to the fact that electrons repel each other. So they don't want to be together unless absolutely necessary, is the idea. They'll only double up whenever there are no more spaces to fill. Now, let's also draw the orbital notation for this example using the shortened version or the noble gas notation. Remember, we can also write noble gas notation using argon as the previous noble gas for chromium. And then after that, we'll write 4s2 and then 3d4. In other words, this portion right here is argon's configuration, so we can represent it using the brackets. And now, we'll still draw one orbital for the s, 5 for the d, and we can fill in the electrons as before. 1, 2, and then 4 in this one. 1, 2, 3, 4. Notice the picture is the same, but we only care about the outer. And usually this will be the case because the inner electrons, remember, do not involve themselves in bonding, so we don't have to consider them when discussing how the atom interacts with other atoms. Go ahead and try an example of each on your own. And I would recommend doing both regular and the noble gas version for this example. And let's finish up with talking about some ideas of these configurations. The first thing we'll define are inner shell electrons, also called the core electrons. And this is exactly what it sounds like. It is the electrons in their inner shell, inside. And these are defined as the electrons that are not in the highest occupied energy level. So here, if you take a look at this configuration, you'll find that we have 3 as the highest shell. And so the electrons below 3 will be the core electrons. In fact, here we have 2, 4, 10. We have 10 core electrons in this case, or 10 inner shell electrons. So let's try that. How many inner shell electrons in these configurations? Well, the highest shell for this first example, the highest shell here is 4. So don't think about 4, but then count all the rest of them. In this case, we have 2, 4, 10, 12, 18. So 18 electrons will be the answer here. If we take a look at cobalt, we could, if we want, to write out cobalt's configuration. That's probably the way to do it. So let's write out cobalt's configuration. Let's do the noble gas. And I would recommend doing the noble gas. Well, in this case, if you do the noble gas, you actually won't see it as well. So let's do the whole thing. we'll have to do cobalt's whole configuration. Cobalt should be the 7th element in the D block. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. And the inner shell electrons then will be the ones not in the highest occupied energy level. This is the highest because 4 is the highest shell. So count everything but these electrons. And that gives us 2, 4, 10, 12, 18, plus 7, 25. So 25 electrons for cobalt. Notice we're practicing writing these configurations over and over again. So try a similar example on your own here. And let's define really the last concept, which is called valence electrons. Now this is the opposite of inner shell electrons. These are the outer shell electrons, the outside electrons. The electrons in the highest occupied energy level. So energy level 3 is the highest here, and you only have 1 electron in the outer shell. So only 1 valence electron, in other words. These electrons, by the way, are the ones that are involved in bonding. These are the bonding electrons. So let's do a quick example. How many valence electrons in these configurations? Let's take a look at the first configuration. Find the highest energy level, which is 4, and you have 1 electron in the highest energy level. So 1 electron here again is the answer, or 1 electron. For this one, the highest energy level again is 4, but we have 2 subshells in the 4, so we have to add up the 2 and the 3 for a total of 5 electrons here. For beryllium and gallium, we can write out the configuration, but let me show you how we can determine it from the periodic table. So take a look at the next slide. So we have beryllium and gallium. Here is beryllium, and here is gallium. Let's first take beryllium. Beryllium's outer shell electrons will be whatever follows helium. Helium and the previous group will be, or the previous period will be inner shell electrons. So beryllium has 1, 2 outer shell electrons. They are situated in the 2s subshell. So beryllium has 2 electrons on the outer shell. If you take a look at gallium, similar thing can be said for gallium. After argon, gallium has 2s2, 3d10, and then, 4s2. These are 4s electrons. This is 3d, and this is the 4p electron. So the 4 is the highest, and you can grab 1 and 2 of these for a total of 3 electrons. If this is confusing, you can go ahead and write out the complete configuration and count them that way. But you could see this from the periodic table, which is important. So go ahead and try an example of this on your own. And the last thing we'll mention about these valence electrons, they're very important. We will study them further. Valence electrons are the electrons involved in chemical bonding. So when these elements decide to come together and form compounds, they will use their valence electrons. Take a look at carbon. If you take a look at carbon, you'll see that carbon has 4 valence electrons. If you take a look at hydrogen, you'll see it has 1 valence electron. Here, carbon's valence electrons are 1, 2, 3, 4. Hydrogen's valence electrons are 1, 1, 1, and 1. And notice they come together to bond with one another, forming the compound CH4. And this is called methane gas, the gas that is used to heat your house, to heat your water, and to do some exciting chemical explosions. All right, this completes for us lesson 7 of chapter 4.